Good morning, everyone. Today I am going to make an audio recording for visually impaired students of Inorganic Chemistry book of Pardeep Publications, Volume 3rd. Name of the chapter is Thermodynamic and Kinetic Aspects of Metal Complexes. The formation of metal complexes in aqueous solutions is a matter of great importance, especially in inorganic chemistry. Invariably, all the metal ions in aqueous solution exist as bracket open M H2O whole N bracket close X positive, where N is the coordination number while X positive is the oxidation state of the metal. The interaction between a hydrated metal ion and a ligand in forming a coordination complex is regarded as a Lewis acid base reaction. The stability of the complex formed is related to thermodynamics and refers to the tendency of formation of a complex at equilibrium. It is appropriate to understand that the stability of a complex compound referred above means that the compound exists and can be stored for a longer period of time under suitable conditions. Thus, the terms stable and unstable are thermodynamic terms representing the tendency of species to exist or not. The term stability referred in the preceding paragraph gives some measure of the final position attained in the equilibrium mixture, but does not give any indication of the time taken to reach the equilibrium point. The term stability can also be used in terms of reaction rates. When reaction rates are considered, complexes can be classified into two general types, viz. Labile and inert. Labile complexes react rapidly, whereas inert complexes react much more slowly. 3.1 Thermodynamic stability of complex ions. Thermodynamic stability of a complex determines the extent of formation of the complex at equilibrium. The stability of the complex depends upon the strength of the bond formed between the central metal ion and the ligands. If the bond formed is strong, the complex formed would be thermodynamically more stable. The thermodynamic stability can be expressed in terms of the equilibrium constant for the formation of the complex. When ammonia is added to an aqueous solution of copper 2 sulfate, there is a noticeable change in the color because the blue Cu2 positive ions are converted to deep blue tetramine copper 2 ions. The reaction taking place can be represented as copper 2 positive plus 4NH3 gives copper NH3 whole 4 2 positive. The equilibrium constant K is given by K is equal to copper NH3 whole 4 2 positive upon copper 2 positive NH3 whole 4 equals to 4.5 into 10 to the power 21 3.1. A high value of K would mean that copper NH3 whole 4 2 positive ion is thermodynamically stable, that is, the equilibrium will lie to the right. Thus, the equilibrium constant K refers to the stability constant of the complex. The higher the value of K, the greater is the stability of the complex. Alternatively, 1 by K values, sometimes called instability constant, is also used. It gives a measure of the extent to which the equilibrium represented in the equation 3.1 lies to the left. A high value of instability constant means that the complex is unstable. Similarly, the stability constant for a related reaction, copper 2 positive plus 4Cn negative, providing copper Cn4 whole 2 negative, can be expressed as K is equal to copper Cn4 2 negative upon copper 2 positive Cn negative 4. The value of stability constant K in this case is 2.0 into 10 to the power 27, A comparison of the stability constants in the above reactions reveal that copper CN42 negative is thermodynamically more stable than copper NH3 whole 2 positive. 3.2 Stability of complexes in aqueous solutions. Suppose we put a hydrated metal ion M and some monodentate ligand L together in a solution. The extent to which the hydrated metal ion combines with ligands to form complex is a thermodynamic problem and can be represented as M H2O whole n plus Nl, providing MLN plus NH2O. In aqueous solution, the concentration of water can be regarded as constant because it changes so little. The reaction thus proceeds stepwise according as M plus L gives Ml, and the equilibrium for constant for the reaction can be expressed as K1 is equal to Ml upon Ml. Now Ml adds to subsequent moles of ligand L as Ml plus L providing Ml2, Ml2 plus L providing Ml3, so on Mln minus 1 plus L providing Mln. There will be n such equilibria where n represents the maximum coordination number of the metal ion M for ligand L. The value of n may vary from one ligand to another. For example, Al3 positive forms AlCl4 negative and AlF63 negative ion, whereas CO3 positive forms COCl42 negative and CONH3 whole 62 positive as the highest complexes with the ligands indicated. The equilibrium constants K1, K2, Kn are known as stepwise formations stability constants or stepwise stability constants. A steady decrease in the value of K is observed in the order K1 is greater than K2, K2 is greater than K3, and so on. This decrease in the value of K is due to the fact that a ligand which is already coordinated to a metal offer repulsion to the additional incoming ligand. This is illustrated for the copper 2 positive NH3, cadmium 2 positive NH3 and cadmium 2 positive Cn negative system. The value of log Ks are given. There is another way we can express the equilibrium relations in terms of overall stability constants as M plus L providing Ml, M plus 2L giving Ml2, M plus 3L providing Ml3, M plus Nl providing Mln. Since equilibrium constant K and stability constant beta describe exactly the same chemical system, they must be related to each other. The relationship between the two can be easily appreciated by inspecting the expression for beta 3. Let us multiply both the numerator and denominator in the expression beta 3 by ml ml2. We get beta 3 is equal to ml3 upon m bracket l whole cube bracket close multiply ml ml2 upon bracket ml bracket close bracket open ml2 bracket close equation 3.2. On rearranging, we get beta 3 is equal to k1 dot k2 dot k3. Similarly, it can be seen that this type of relationship can be written for beta n. Beta n is equal to k1 dot k2 dot k3 and so on till kn. It can also be simplified by writing beta 3 is equal to pi ki. The Ki are called stepwise formation constant or stepwise stability constant, and beta I are called overall formation constant or overall stability constant. Taking log on both sides of 3.4, we get log beta n is equal to log k1 plus log k2 plus log k3 plus log kn. Thus, log beta n is generally used as a measure of stability of the complex. the values of log beta 4 in case of copper NH3 whole 4 2 positive is log beta 4 is equal to log K1 plus log K2 plus log K3 plus log K4. 4.30 plus 3.60 plus 3.10 plus 2.30 equals to 13.30. Cadmium NH3 whole 4 2 positive is log beta 4 is equal to 2.65 plus 2.10 plus 1.44 plus 0.93 is equal to 7.12. A comparison of the log beta value of the amine complexes of copper and cadmium indicate that copper NH3 whole 4 2 positive complex is more stable than cadmium NH3 whole 4 2 positive. This explains clearly to us why copper 2 positive ion does not precipitate out as copper S when H2S gas is passed through a solution containing copper NH3 whole 4 2 positive complex, whereas cadmium 2 positive really form yellow precipitate of CDS when H2S gas is passed through a solution containing CdNH3 whole 2 positive. The numerical value of a stability constant describes the relative concentrations of species at the equilibrium. The larger value of stability constant indicate that the concentration of the complex is much greater than the concentration of the components of which it is made of. In other words, the complex is stable if the equilibrium constant displaying its formation is large. A low K value greater than 8 suggests the complex to be stable. Similarly, thorium Th4 positive can be determined in the presence of divalent cations using EDTA4 negative. The analysis of thorium is possible because of the large difference in formation constants for the EDTA4 negative complex of 4 plus 2 plus cations. 3.3 Factors affecting the stability of complexes. Complexes are formed by the interaction between a metal ion and the ligands. The stability of the complex depends upon several factors, of which two are of primarily importance. First, nature of central metal ion. Second, nature of the ligand. Let us first discuss as to how the central metal ion affects the stability of the complex. The stability of the complex depends further upon a. Size of central metal ion. Small sized metal ions form stable complexes. The stability of the complexes increases with decrease in the ionic radius of the central metal ion. B. Charge density on the central metal ion. Charge density means ratio of the charge to the radius of the ion. Charge density is higher in cases where the size of the ion is small and carries high charge. It has been found that complexes formed by metal ions with high charge density are more stable. A smaller and highly charged ion can approach the ligands more closely. As a result, there is greater attraction between the metal ion and the ligands, which results in the formation of a stable complex. In brief, stability of the complex increases with the increase in charge on the central metal ion. This is evidenced by the fact that complexes Fe3 positive ion are more stable than those of Fe2 positive ion. As summarized, complexes with large overall stability constant are more stable. Combination of A and B above shows that it is the charge by radius ratio which is significant. A large charge by radius ratio leads to a stable complex. C. Electronegativity of the metal ion. Electronegativity of the metal ion plays an important role in determining the stability of the complex. On the basis of electronegativity, metal ions can be classified broadly into two classes. This concept of classification of metal ions was introduced by Ireland, Chat, and Davis accordingly. Class A metals includes the alkali and alkaline earth metals, first transition series, and lanthanides and actinides. Class B metals includes heavy metal ions. These heavy metal ions contain large number of d electrons beyond an inert gas core. Similarly, other heavier electronegative metal ions such as Hg2 positive, Pb2 positive, Cd2 positive cations form insoluble sulfide salts. The formation of these stable salts indicates that these metals prefer sulfur containing ligands due to considerable covalent character in metal sulfur bond. Second, nature of the ligand. The stability of the complex also depends upon the nature of the ligands. Some of the important factors associated with the ligands are A. Size and charge of the ligand. The size and charge of the ligand determines the stability of the complex. For example, the smaller F negative ions form stabler complex than the large Cl negative ion, as is evidenced by the stability constant of the complex formed. Complex FeF2 positive log beta 6, complex FeCl2 positive log beta 1.3. It means that the larger ion, that is Br negative, I negative, ClO4 negative, should be less stable. In fact, larger ions have little tendency to form stable metal complexes. Similarly, the small di-negative ion O2 negative prefer to form stable complexes compared to large S2 negative ion with class A metals or electropositive elements. In brief, class A metals form stable complexes with strong electron donors. Third, basic character. The basicity of the ligand plays an important role. The greater the ease with which the ligand donates electron pairs, the greater is the stability of the complex formed by it. Basicity of a ligand determines how easily it can donate electrons. A strong base is a good electron donor, and many common ligands like Cn negative, F negative, and NH3 are also strong bases. In other words, the greater the base strength of the ligand, the greater will be its tendency to form stable complex. The base strength of a molecule determines the stability of the complex that the molecule forms with the H positive ion. It means the ligand which bonds H positive ion firmly should form stable complex with metal ions. There is something common in the formation of an acid and complex ion, as H positive plus base produce acid, M plus ligand produce complex. Thus, F negative ion should form more stable complexes than Cl negative, Br negative, or I negative ions. Similarly, NH3 should be a better ligand than H2O. This type of behavior is elegantly observed for class A metals, that includes alkali metals, alkaline earth metals, first row transition metals, lanthanides, and actinides. However, it is not true for class B metals, that is, ions of more electronegative elements with Au, Pd, Pt, Hg, Pb, etc. Class A metals attracts electrons weakly and form more stable complexes with ligands containing N, O, and F atoms. On the other hand, class B metals form more stable complexes with ligands containing P, S, Br, and I atoms. Such ligands containing P, S, Br, and I atoms are capable of accepting pi electrons from the metal atoms. In between these two classes, there are metal ions that possesses intermediate character in forming complexes. Such metal ions are referred to as borderline metals. Common example of borderline metals are Mn, W, Ti, Pb, etc. The bonding between a central metal ion and a ligand is due to donation of electrons by the ligands to the central metal ion. A strongly electron attracting metal ion, that is, a metal ion with high electronegativity, is expected to form stable complex. Electronegative metals, such as those of copper family, that is, copper, Ag and Au, zinc family, that is, Zn, Cd and Hg, together with Pd, Pt, Rh, Ir, Pb, etc., form stable complexes through covalent bonding. For example, silver forms insoluble halides such as AgX and stable halides complexes AgX2 negative, in which the order of stability is I negative more than Br negative more than Cl negative more than F negative. In brief, the covalent character accounts for the stability of silver halides as one goes from F negative to I negative. C. Presence of ring structure chelation. The stability of the complexes is greatly increased by chelation. Chelates are cyclic or ring compounds that are formed when a ligand binds the central metal atom or ion through two or more donor atoms of a ligand. Such a ligand which binds the metal atom through two or more atoms is called a chelating ligand, and the process is called chelation. Chelated complexes formed by multidentate ligands such as En, ACAC negative, TER, or EDTA have been found to be more stable than those formed by monodentate ligands such as H2O, NH3, or pyridine, or C2H5N. This increased stability of the complex containing chelating ligand is called the chelate effect. As an example, the stability of nickel complex with chelating and non-chelating ligand is given below. This increased stability of the En complex of nickel over the ammonia complex can be easily explained in terms of favorable entropy during chelation as shown below. NiH2 whole 62 positive plus 6NH3 providing NiNH3 whole 62 positive plus 6H2O. NiH2 whole 62 positive plus 3N providing NiEN whole 32 positive plus 6H2O equation 3.7. During complexation with ammonia, 6 ammonia molecules displace 6 water molecules as represented in equation 3.6, and there is no change in the number of molecules. However, during complexation with En, 3 molecules of En displace 6 ammonia molecules as represented in equation 3.7, and there is an increase in the number of molecules particles on the right hand side of the equation. In other words, the entropy of the system increases. This increase in the number of molecules decreases the order in the system, and consequently the entropy of the system increases. In brief, the stability of the chelated complex can be explained due to an increase in the entropy of the system. Second, number of chelate rings. A chelate in which more number of rings are formed is more stable. In other words, the larger the number of chelate rings in a complex, the greater is the stability of the complex. A comparison of the stability constant for some complexes is given below. CuNH3 whole for 2 positive, number of chelate rings 0, log beta value to 12.6. CuEn whole 2 positive, number of chelate rings 2, log beta value 20.0. Cu triene whole 2 positive, number of chelate rings 3, log beta value 20.5. Where TRIEN is triethylene tetraamine. For sake of clarity, the chelating behavior of triene towards Cu2 positive ion depicting 3 rings is shown. Third, size of chelate rings. The stability of the chelate depends primarily upon the size of the ring formed. Unlike organic ring systems, metal chelates with 5-membered rings have been found to be more stable. This is because the metal atoms are larger in size than the carbon atoms in organic molecules. In addition, the bond angle the metal atom form in square planar or octahedral complexes are 90° in contrast to optimum angle of 109 degree point 5 minute for carbon in conventional organic compounds. A number of stable 5-membered chelate rings are formed with various chelating ligands with ethylene, diamine, oxalate ion, glycine, and dimethylchloroxine. It is important to mention that only those 5-membered chelates are more stable than 6-membered chelates, where atoms on the rings are joined only by the single sigma bonds. However, chelating ligands such as acetylacetone forms stable 6-membered rings having double bond or unsaturation in the rings. For example, acetylacetone forms neutral complexes with trivalent metals such as TiACAC whole thrice, CrACAC whole thrice, and COACAC whole thrice. In these complexes, the rings are symmetrical with the MO bonds equal in length. The CO bonds and the two CC bonds are equal in length as a result of resonance equivalence. Rings of size greater than 6 are known but not very stable. The instability of the higher membered can be attributed to the extra energy required to bring the coordinating atoms of the ligand closer to the metal ion for bonding against electrostatic forces. Decreased effective concentration of the other end of the ligand for large chelating molecules that form 7 or 8 membered rings. Scarcity of finding sterically non-crowded ring formation. Fourth, steric effects. Ligands containing larger bulkier groups form less stable complexes than the smaller groups. This is because the bulkier group present near a donor atom cause mutual repulsion. As a result, the metal ligand bond becomes weaker and accounts for the reduced stability of the complex. This effect is called steric hindrance. For example, En forms stabler complex than those of the corresponding bulkier tetramethyl substituted derivative, that is CH3 whole twice NCH2 CH2N CH3 whole twice. Similarly, nickel 2 positive forms a stable complex with 8-hydroxyquinoline bracket also called oxine bracket close and a less stable complex with sterically crowded ligand 2-methyl 8-hydroxyquinoline bracket Me oxine bracket close. Question 1. Why 2-methyl 8-hydroxyquinoline nickel complex is less stable than 8-hydroxyquinoline nickel complex? Answer. It is because of steric hindrance. Question 2. Why N dash, N double dash, and triple dash tetramethylethylene diamine complexes with transition metal ions are stable than the ethylene diamine? Answer. It is due to steric effect. In fact, the donation of electrons by the nitrogen atoms bring the methyl groups closer, which causes weakening of the metal ligand bond. Question 3. Distinguish between the chelating ligands tren and trien. Answer. TREN is 2, 2 dash, 2 double dash triamino triethylamine, that is bracket NH2 CH2 CH2 whole thrice bracket close N, and TRIEN is triethyl triethylene tetraamine NH2 CH2 CH2 NH CH2 CH2 NH CH2 CH2 NH2. Question 4. Why the chelating ligand trimethylene tetraamine TRIEN forms a square planar complex easily compared with the chelating ligand 2, 2 dash, 2 double dash triamino triethylamine TREN? Answer: triethylene tetraamine (TRIEN) can coordinate its 4 N atoms to a metal atom situated at the corners of a square to form a square planar complex easily. However, TREN, that is 2, 2 dash, 2 double dash triamino triethylamine, cannot coordinate simultaneously its 4 N atoms due to its geometry to the metal atom. As a result, TRIEN forms the square planar complex easily than the TREN. Much of the work on square planar complexes has been focused on platinum 2 compounds because platinum 2 complexes are stable, relatively easy to synthesize, and undergo ligand exchange reactions at conventionally measurable rates. A substitution reaction involves the replacement of one ligand in a complex by another external ligand without any change in either the oxidation state or the coordination number of the central metal atom. A typical substitution reaction of Pt2 is PtCl4 negative plus 3NH3 provides PtNH3 whole thrice Cl negative plus Cl negative. PtNH3 whole 4 2 positive plus Cl negative provides PtNH3 whole thrice Cl positive plus NH3. There are several pathways by which the substitution reactions of square planar complexes proceed. The important three ways are: first, dissociative pathway. A dissociative pathway is the one in which the leaving ligand is given up in the initial reaction step, forming an intermediate of smaller coordination number mxn, providing mxn-1 providing mxn-1y. In the dissociative mechanism, bond breakage is an important process. Reactions of the SN1 type are thus classified as D. Associative pathway. An associative pathway is the one in which the entering ligand is added to the initial reaction step, giving an intermediate of the larger coordination number as mxn, providing mxny, providing mxn-1y. In the associative mechanism, bond formation is an important process. Reactions of SN2 types are thus classified as A. Third, interchange pathway. An interchange pathway is the one in which the leaving ligand Y is moved from the inner coordination sphere to the outer sphere and the entering ligand is moved from the outer sphere to the inner one, as mx4y providing mxn-1yx, where the dotted lines indicate separation between inner and outer spheres. In the interchange mechanism 1, both bond breaking and making is an important process. If the former predominates, the mechanism is designated as ID, that is, interchange through dissociation. However, if the latter predominates, the mechanism is designated as IA, that is, interchange through association. 3.5 Rate law for nucleophilic substitution in square planar complex. Let us consider a typical nucleophilic substitution reaction in a square planar platinum 2 complex bracket PtL2TX bracket close plus Y gives PtL2Ty plus X, in which Y is the entering nucleophilic ligand, X is the leaving ligand, and T is the ligand trans to X. The concentration of the incoming nucleophile Y is very large compared to that of the platinum complex PtL2TX. It means that Y practically remains constant. It has been experimentally found that the observed rate law in square planar complexes is rate is equal to minus dptL2tx upon dt equals to k1 PTL2TX plus K2PTL2TXY equation 3.8, where PTL2TX is equal to concentration of the complex formed, Y is equal to concentration of the equation on rearrangement becomes rate is equal to K1 plus K2Y, PTL2TX is equal to K observed PTL2TX, where K observed is equal to K1 plus K2Y equation 3.9. The values of K1 and K2 can be determined by carrying out the reactions at various concentrations of Y. A plot of K observed versus concentration comes out to be a straight line with K1 as the intercept and K2 as the slope. Typical plots of the variation of rate constant K observed for a 4-coordinate square planar PT2 complex undergoing substitution by a number of nucleophiles in a coordinating solvent MEOH are shown in figure 3.1. The rate law can be rationalized in terms of two parallel pathways, both involving in an associative mechanism. The term K2 indicates direct nucleophilic displacement of X by Y. The reaction is first order with respect to both the complex and the nucleophile Y. This closely demonstrates associative pathway, which is similar to biomolecular nucleophilic substitution SN2 reaction. The term K1 represents that the reaction is first order with respect to the complex and is independent of Y. It indicates a dissociative pathway. However, there are strong evidences which suggest that this pathway is also associative due to the coordinating nature of the solvent. In fact, the solvent S behaves as a nucleophile and competes with the incoming nucleophile Y for the platinum complex PTL2TX to form PTL2TS. PTL2TX plus S, slow process PTL2TXS. The rate law for this reaction can be written as rate is equal to K dash bracket PTL2TX bracket close bracket S bracket close plus K2 bracket PTL2TX bracket close bracket Y bracket close equation 3.10. Since the quantity of the solvent is very large, the concentration of the solvent S practically remains constant and we can formulate K dash S is equal to K1. Therefore, the equation 3.10 simplifies to equation 3.8. The two associative pathways can be compiled up as the first path K1 represents a two-step process in which the solvent S is first replaced in the rate determining step. This K1 path obeys first order kinetics. The Ki path is completed when the intervening solvent ligand is replaced by X. The second order path is characterized by the rate constant K2. Both the path appears to involve associative activation and A or IS mechanisms for each step of either the K1 or the K2 paths are assigned. There is another approach in which the term K1 in the rate law can be visualized. According to this approach, K1 can also arise because of the dissociation pathway resulting in a 3-coordinate complex, which can react further with Y as shown to give the substituted product. In view of this dissociation pathway, the rate law expression cannot distinguish between an associative A and dissociative mechanism D for the K1 pathway. This uncertainty in the interpretation of K1 term can be resolved by setting up different experiments. A great deal of evidences has been collected in favor of the associative mechanism through many experiments which are outlined below. The reactions have been found to occur faster in more nucleophilic solvents. It suggests that the solvent plays an important role. The dissociation reaction should speed up in the presence of sterically demanding ligands. However, in practice, the reaction rates are lowered. It suggests that the reaction proceeds by associative mechanism A. Thermodynamic studies also favor the associative mechanism in square planar nucleophilic substitution reactions. 3.6 Trans effect. The presence of large deposits of platinum ores in Russia resulted in detailed study of the coordination compounds of platinum. As a result of these studies by the Russian researchers, the first stereospecific displacement reaction on platinum 2 complex was discovered. The pioneering work in this field was initiated by Russia, who introduced the concept of trans effect in platinum complexes. The work was later extended by Chad Ducanson and Vanzicki UK in the early 1950s. What is so unique about this trans effect? It was experimentally found in square planar substitution reactions that by changing the nature of the ligand, it is possible to change the rate of the reactions in many orders of magnitude. It has been found that in square planar complexes of platinum 2, the ligand trans to the leaving group has a very strong effect on the rate of the substitution in comparison to ligands cis to the leaving group. Because of the preferential behavior of trans ligands, this effect is popularly called trans effect. The trans effect may be defined as the labelization bracket easier displacement bracket close of ligands trans to other trans directing groups. Such a group has a marked effect on the rate of the reaction. Let us consider the formation of dichlorodiamine platinum 2 complex PtCl2NH3 whole twice. This square planar complex can exist in two isomeric forms, cis isomer, trans isomer. The stereochemistry plays an important role and affects the chemical reactivity of two isomers of the platinum 2 compound. The cis isomer is effective as a therapeutic drug and is extensively used in the treatment of cancer. The two isomers can be prepared either by first replacement of Cl negative ion in PtCl4 2 negative by NH3 or second replacement of NH3 in PtNH3 whole 4 2 positive by Cl negative ion. Let us first study the replacement of Cl negative ion in PtCl4 2 negative by NH3. Reactions in equation 3.11 can be rationalized as follows. In the first step, simple displacement of the Cl negative ion by NH3 takes place. Since all the four groups present in the starting material, PtCl4 whole 4 negative, are chloride ions, only one compound is formed. In the second step, two products can potentially be formed. However, in practice only one product, that is cis PtCl2NH32 is formed, in which the substitution of a ligand occurs trans to Cl negative ion. For sake of clarity, the ligand trans to Cl negative has been circled. Let us now study the reaction of replacement of NH3 in PtNH34 2 positive by Cl negative ion. Reactions in equation 3.12 can be rationalized as follows. In the first step, simple replacement of one ammonia molecule by Cl negative ion takes place. Since all the four groups present in the starting material PtNH342 positive are identical ammonia molecules, only one product is formed. In the second step, two products are possible, however, only one product is exclusively formed, in which substitution of ammonia occur trans to chloride ion Cl negative. In both the reactions 3.11 and 3.12, however, the exclusive isomer formed is the one in which substitution of a ligand occurs trans to the chloride ion. The ligands trans to the chloride ion have been circled in equation 3.11 and 3.12 to highlight this important called trans effect. Thus, trans effect is defined as the labelization easier displacement of ligands trans to other trans-directing ligands. By investigating a large number of reactions, it is possible to compare the trans-directing influence of a variety of ligands. Let us consider a case where Two ligands A and B can labelize a trans Cl negative ion with the same entering ligand NH3. We can get either product 1 or 2 depending upon the greater trans directing influence of A or B. On the basis of trans directing group, different ligands can be arranged in the following decreasing order in the substitution reactions of platinum 2 compounds: Cn negative, CO, NO, H negative, CH3 negative, SCNH2 whole 2 SR2, PR3, SO3H negative, NO2 negative, I negative, SCN negative, Br negative, Cl negative, Py, RNH2, NH3, OH negative, H2O. A careful glance at the above order indicates that Cn negative, CO, NO, and H negative are powerful trans-directing ligands, whereas OH negative and H2O are the poorest trans-directing ligands. It is furthermore important to mention here that all the examples of the trans effect are majorly restricted to square planar platinum 2 complexes. The order of the trans effect of the ligands depends upon the nature of the complex. It can also be derived from the rate constants of the reactions. The rate constants for the substitution of the ligands in case platinum 2 complexes are tabulated in table 3.1. Table 3.1. Trans effects of various ligands and rate constants. Reaction rates very large. Approximate rate constant K 10 to the power 5. Reaction rate large. Approximate rate constant K 10 to the power 2. Reaction rate moderate. Approximate rate constant K 10 to the power 0 equals to 1. Reaction rate small. Approximate rate constant 10 to the power minus 1. Trans effect in synthesis. The trans effect has been used in preparing the desired isomer, which otherwise is very difficult to prepare. As already explained, the cis and trans PTNH3-2Cl2 complexes can be prepared by a definite sequence of addition of substituents, keeping in view that the Cl negative ion has a greater trans effect than ammonia. In case of PtCl4 negative complex, the second ammonia molecule replaces the chloride ion at the cis position because the trans-directing influence of Cl negative ion is far more greater than that of ammonia, NH3. Similarly, in case of PtNH3 whole for 2 positive complex, the second Cl negative ion replaces the ammonia molecule at the trans position because of the strong trans-directing effect Cl negative ion. Using similar reasoning, it is possible to prepare all the three isomers of square planar amine bromochloro platinum 2 by following the sequences of reactions as given below. In addition to trans effect, we must remember that the metal halogen bond is more labile than the metal nitrogen bond. Taking into account the more labile nature of metal halogen bond, the chlorine trans to another chlorine will be replaced more readily than a nitrogen trans to chlorine. The group trans to the most influential trans director is circled again. It is important to note that in step 3, the bromide ion is a better trans director than the chloride ion, and consequently the chloride ion is replaced with pyridine in isomer 1. In this case again, the lability of the metal-chlorine bond results in the preferential replacement of the chlorine instead of pyridine in the second step. As a result, trans influence of bromide ion determines the final geometry of the isomer 2. In the preparation of isomer 3, the trans effect predicts the formation of cis isomer in the second step. The replacement of ammonia trans to the chlorine in the third step occurs more readily than the replacement of pyridine trans to the chloride ion. It is due to the labile nature of PtCl bond. In the last step, however, the lability of PtCl bonds runs opposite to the stabilizing trans effect. An interesting application of the trans effect is that it helps in distinguish the cis and trans isomers of complexes of the type PTA2X2, where A is equal to amine and X is equal to halide. This is called Konakov Test. It involves the addition of thiourea to the complex under examination. If the complex PTA2X2 is cis, it results in the complete replacement of the former ligands. But if the complex PTA2X2 is trans, the replacement stops after the two halide ions have been replaced. This is because trans ammonia molecules do not levelize each other. 3.7 Mechanism of nucleophilic substitution in square planar complexes. We have already discussed that D8 square planar complexes Ml2Tx undergo bimolecular displacement reactions. The incoming nucleophile can attack the metal atom from either side, above or below the plane of the square plane in the z direction and forms a 5 coordinated square pyramidal intermediate. The substitution reactions thus invariably proceeds readily through an increase in the coordination number of the central metal ion. Although the nucleophile bracket being short of electrons bracket close is attracted by the electron deficient metal atom, it faces repulsion from the filled metal d orbitals and the associated bonding electrons. The incoming ligand prefers to coordinate to the metal atom through vacant pz orbitals. This square pyramidal intermediate rearranges itself into a more favored stable trigonal bipyramidal TBP structure. This TBP arrangement has three ligands T, X, and Y in the equatorial plane and two ligands trans to each other in the axial plane as shown in figure 3.2. As the leaving group X departs from the trigonal plane, the angle TMY opens up. This results into a square planar product ML2TY with the release of X as shown in figure 3.2. The trigonal bipyramidal geometry that forms during the course of the reaction rearranges to give the product V that may exist either as an activated complex or as a true intermediate. 3.8 Theories of trans effect. Trans effect basically deals with the kinetics of the reactions and provides qualitative information on the rates of the reactions in square planar complexes. This effect also plays a very important role in determining the stereochemistry of square planar complexes. A number of attempts have been made to explain this effect. Two main theories have been proposed: polarization theory, second, pi bonding theory. Before we discuss the various theories, it is appropriate to recall that trans effect deals with the rate of the reactions. Therefore, energy of activation must be playing an important role. We know that energy of activation basically determines the difference between the energies of the reactant in ground state and the first transition state. Thus, any change in the energy of the reactants in the ground state and the first transition state affects the activation energy and consequently the stability of the system. The relationship between the energy of the reactants and that of the activation complex is shown in figure 3.3a. The energy of activation for a reaction can be lowered in two ways. First, by increasing the energy of the ground state of the reactants, figure 3.3b. Second, by decreasing the energy of the transition state, figure 3.3c. First, polarization theory was suggested by Greenberg. According to Greenberg, in a completely symmetrical complex such as PtCl4 2 negative, the dipole moments of all the bonds will be the same and there will be no net effect. However, if a more polarizable ligand T is introduced, such as I negative, its polarizability will induce an additional uncompensated dipole in the metal. This induced dipole in the metal will oppose the nature dipole of the ligand trans to the polarizing ligand. The polarization theory is supported by the following facts. First, trans effect is most important with the large and polarizable metal ions. The order of the metals being Pt2 greater than Pd2 greater than nickel 2. Second, trans-directing groups are more polarizable as they are large. Example, iodide ion or multiple bonded systems such as CO, Cn negative, etc. Thus, the induced dipole repel negative charge density in a bonded ligand L, which reduce the attraction between Pt and L. This results in the lengthening and weakening of Pt-L bond, which has been clearly explained on the basis of X-ray studies. For example, the PTCl distance in trans PTCl to ET3P2 corresponds to 2 to 9.4 ppm. On the other hand, in cis, where Cl is trans to trimethylphosphine Me3P, the PTCl distance increases to 236.4 and 238.8 pm. It clearly demonstrates that the trans-phosphine ligands weakens PTCl bond as compared with the Cl negative ligand in the second pi bonding theory. A second approach that involves the weakening of the trans bond is the static pi bonding theory. According to this theory, trans-directing ligand is capable of accepting pi electrons from the central metal. Figure 3.5 explains the interaction of pi acceptor orbitals on ligands such as CO and C2H4 with a transition metal that is believed to result in a weakening of the trans metal ligand bond. The pi bonding results in a reduction of electron density in the interligand region. This makes nucleophilic attack much easier. In addition, such a pi bonding interaction stabilizes the 5 coordinate intermediate or activated complex, as is evidenced in associative mechanism where L is replaced by incoming ligand.